So we're going to turn our attention to the nucleus of the atom. And what we do is we're going to look at changes in that nucleus. And when the nucleus changes, it's going to go through some sort of decay process. And that's typically because it's unstable. The ratio of protons to neutrons is not where it should be. And these atoms, the nucleus, if you think about the nucleus really in electrostatic forces, the nucleus is composed of neutrons and protons, right? There's no electrons in there. And what do we know about like charges? Right, they repel. So there has to be something overriding that repulsion, them pushing apart. And that's another force that's out there. So you have gravity, right, which is a gravitational force. You have electrostatic forces. The thing that holds the nucleus together is called a strong force. There's also a weak force in there too, but we don't get into that one in this course. Like that's upper level physics-y kind of wacky stuff that we don't have the math, including me, to deal with. Some of you will have the math someday, but you know, we're not there yet. So, but the strong force is what holds that together. If the ratio of protons to neutrons gets off too much, that strong force can't hold it together, and it starts going through this decay process. Okay, so we call this nuclear chemistry because it's dealing with the nucleus of the atom. All right, so like I was saying, it's a reaction that's going to change an atom's nucleus. The radioactive atoms emit radiation because their nuclei are unstable. The nucleus should push apart, but we have these strong forces that are going to override that. But they only work over stupidly small distances. So remember how tiny we talked about the atom being last week? We said that the nucleus was like a marble in the middle of a football stadium. Okay, that's super. I mean, think about the size of an atom, and now think about the size of the nucleus compared to the atom. I mean, that's stupid tiny, and that's where these strong forces are working. So it's like almost inconceivable how tiny that distance is. All right, so radioactive elements, there are several types of nuclear radiation. We're only going to look at 3 of them. One of them is called an alpha, which is essentially a helium nucleus. It's 2 protons and 2 neutrons. We look at beta, which is essentially an electron. And then the last one is gamma, which is just pure energy. So you know how you have light waves? And then above light waves are UV rays, right? The stuff that damages your skin from the sun. And then you've got X-rays, and then above them is gamma rays. So super, like lots of energy involved in those. All right, so alpha is going to contain 2 protons and 2 neutrons. It's going to have a 2+ charge. Okay, and that probably should be actually superscript there, sorry. Sorry about that. This is the abbreviation for it. So it's like a kind of like a fish, if you were to draw kind of a fish, a lazy fish without the tail being connected at the end. Okay, if you're as bad a drawer as I am, that's how you draw fish. You do a shoot and then all right, this will do a lot of damage if it's allowed to penetrate the body. So if you get it inside your body, it's going to cause a lot of damage. But a lot of times your skin can stop it, or just a piece of paper would actually stop the alpha radiation. They're big enough particles that they can get stopped by just that. If you ingest this, though, it's a big deal. So if you've ever seen or heard of the radium girls at all, okay, they were people who painted dials on watches back in like the early 1900s, and they would work with paintbrushes. And so they would dip it down in this radioactive material because they didn't realize that it was a bad thing then. And then they would take the brush tip, and after they had painted it, they would take it and lick it to make it a sharp point, and then dip it back down in there and paint the dials. And they were putting that directly into their mouth, and like their jaw would disintegrate over time. Like they said that, like one of the dentists said that he actually reached in the person's mouth and just removed their lower jaw. Like didn't have to do any surgery, nothing. I mean, it was that decayed and eroded. So lots of damage if it gets in, but typically, you know, you're pretty safe with this because you're probably not going to ingest this stuff. All right. This is what an equation would look like for these. And if you think about these equations, when you're working with these, you can kind of think about them being in two different steps. So don't write down what's up there. Pay attention to me first and then go back and write it down. Okay? So pay attention and then write it down. All right. So if I'm starting out with Ra226, okay, this is its mass number. What is a mass number again composed of? What, two protons and neutrons. Okay. Do you have a pass, honey? Who said? Joyce? Okay, that's fine. All right, so when you look at these, this top number is your protons and your neutrons combined. So if we subtracted this value, this is our atomic number, which is the number of protons. If we subtract this from this, then that's going to give us our neutrons. Okay, just as kind of a reminder. But think of this equation in two different halves. So you've got your top half here. Okay. And if you look at this, if you look at it like just kind of a simple math equation from back in elementary school, okay, I oftentimes will say, okay, you're going to have this. It's going to have an alpha particle. This is what an alpha particle looks like. It's going to have an alpha particle come off. So if you had 226 equals blank plus 4, what would go here? 222. Okay, makes sense? All right, so that's where they got that 222 here. And then if you look at the bottom part of the equation, it's the same thing. So 88 equals blank plus 2. So what goes here? 86. And then you look at your periodic table to figure out what element to put here. So if you look at number 86 on your periodic table, it is Rn. And that's where they get the numbers for these. So if I said uranium 238, it's 92. Yeah. Uranium 238 gives off an alpha particle. This is our alpha particle. What would go here? Do that problem. Yeah. Yeah. All right, let's see what you got here. This is probably gonna, no, it did not. Good. Okay. So what would our top number be here? 234. Okay, because 234 plus 4 equals 238. And what would my bottom number be? 90, because 90 plus 2 gives us 92. And then element 90 is it PA? Okay, I don't have my glasses.
Thorium.
TH. Okay, sorry. If I don't have my glasses on, I'm kind of a fish out of water. All right, does that make sense? Okay. So what they would say is like uranium, which I should have had uranium here, uranium 238, and this is 238 uranium. We get the 92 off the periodic table. So uranium 238 gives off an alpha particle. What is its daughter isotope? Okay, and that you would say thorium 234. Does that make sense? Okay. All right. So that's alpha. Beta then is made up of an electron. Now, remember back, I told you back when we were looking here, I said, remember, I want you to remember me talking about this, where our neutron is slightly heavier than our proton. Do you remember me talking about that? And I said, I want you to hold on to that nugget because we're going to come back to it. Well, essentially what a neutron is it's a proton and electron stuck together. Okay? And that's why the mass here is just slightly heavier. Because the proton is so much bigger than the electron. When you add it in, it doesn't add a whole lot, but it adds just a little bit. Okay? So that's where that comes from. So when we go through beta decay, essentially what's happening is you're having a neutron is splitting into a proton and an electron. The electron then zooms out of the nucleus, and that is your beta particle. It has a -1 charge. It has no mass. It's abbreviated like a capital B with a little tail on it. And this can be stopped by a piece of aluminum foil. All right, so here is what happens with this. Okay, we've got carbon. It's carbon 14. We're going to give off a beta particle. When we write down a beta particle, the beta particle is 0, -1, and then we write down an E here. What do you think that E stands for? Electron, right? Okay. Now, if I had a math problem and the top part was 14 equals blank plus 0, what would my blank? 14. All right, now this one's a little harder, but not bad. 6 equals blank plus -1, 7. And then you look on your periodic table and find number 7. It is nitrogen. Okay, now let's talk about why that's the case. Okay, when we have carbon here, carbon 14 looks like this. We have our electron, or our protons here. We've got 6 of those. 14 minus 6 is what? 8. So we've got 8 neutrons. Now remember, a neutron is essentially an electron and a proton stuck together, right? Okay. So if I take and I have my electron go away, it's gone off into the wild blue yonder. Now, look what I have. See what happened there? Okay. So here, now I've got 7 protons. I've got 7 neutrons. My mass number didn't change because remember my mass number is protons plus neutrons. So if you trade a proton for a neutron, your mass is not going to change. Okay, does that make sense how this guy kind of, he's gone? Okay, so that's what happens with your numbers, and that's how you do that. All right, the last thing that we're going to look at today then is gamma radiation. Gamma radiation is pure energy. Again, this is like your X-rays, your microwaves, your radio waves, those types of things, okay? So when we look at electromagnetic radiation, it is a spectrum. Let me find an image here that I can pull up for you guys. So it's all a spectrum, okay? Visible light is part of that. It's a tiny part right in here of that. You've got your UV, your X-ray, and then your gamma come up here. And the difference between these is the frequencies, how fast that energy happens to hit you. So for radio waves, it's not going to hit you very fast, so you don't get a lot of energy. So it's just like boom, boom. But when you get up to gamma rays, it's like rapid, and it's going to cause damage when that happens. UV is here. X-rays are even worse, and gamma rays are way worse than that. Anything above here is called ionizing radiation, and it's because it'll cause ions to form that shouldn't. And then you get things like reacting in places that they shouldn't be reacting. And that's part of the reason why you get cancer from these types of radiation. Infrared is heat. Any of these things that you get in too much of a quantity can cause problems. Okay. For example, you get too much heat, you can die. Microwaves. You wouldn't want to be in a microwave. That's too intense for us. We wouldn't be able to handle it. Okay. And then you've got radio waves, which are not as bad. But gamma is what we're looking at right now as far as being nuclear. So this is going to contain pure energy. It does not have a charge at all. And it's like a kind of a fancy looking Y, uppercase Y for its abbreviation. It's going to be stopped by several inches of lead. So when you go to the dentist and they give you X-rays, or when you go to other X-rays, they put that lead vest on you. Okay. That's just like that thin, okay? That stops X-rays. Gamma rays, you need several inches of lead. Okay, your body would not be able to handle the weight of that. I mean, that apron that they put on you when you get dental X-rays is heavy enough. You're like, wow, that's kind of heavy. But several inches of lead, like, that's just on the level of stupid. So, all right. So when we're doing these are pretty easy. If it gives off gamma, it just looks like this, and there should be a plus sign in between here that I obviously neglected to put on there. So apologies there. Okay, questions on these? And I think the next one is the decay. Yeah, that's it for here. So. All right, good. Did I not put half-life notes on here? I must not have. I need to go back and do that. Yeah.
What kind of radiation is used for cancer?
Well, chemo is different. That's like chemicals. That's like chemicals that are they insert into your body. I will have to look that up. Give me just a minute here to